When you look up at the night sky, you're not just seeing stars twinkling in the present moment. You're actually looking back through time. Every photon of light that reaches your eye has traveled across space for years, sometimes millions or even billions of years. The universe is like a cosmic archive, and tonight we're going to take a journey through it, from the newest babies of creation to the ancient relics that have witnessed nearly everything. Think about it this way. If you could arrange every object in the universe by age, you'd have a timeline stretching from things that formed yesterday to objects that are nearly as old as time itself. And that's exactly what we're going to do. We're going to travel through cosmic time, meeting the youngest stars, the middle-aged galaxies, and finally, the oldest structures we can possibly detect. This concept of looking back in time isn't just a metaphor. It's literally what happens when we observe the universe. Light travels at a fixed speed, about 186,000 miles per second. That's fast, incredibly fast, but space is so vast that even at that speed, light takes time to travel from one place to another. The light from the sun takes about 8 minutes to reach Earth. The light from the nearest star after the sun, Proxima Centauri, takes 4.2 years. The light from the Andromeda galaxy takes 2.5 million years. So when you look at the sun, you're seeing it as it was 8 minutes ago. When you look at Proxima Centauri, you're seeing it as it was 4 years ago. When you look at Andromeda, you're seeing it as it was during the time when our ancestors were evolving in Africa, learning to use stone tools long before civilization existed. This means the universe is its own history book. The farther away we look, the farther back in time we see. And if we look far enough, we can see all the way back to the beginning, to the cosmic microwave background radiation that filled space just 380,000 years after the Big Bang. This isn't going to be a quick tour. We're settling in for the long journey, because the story of cosmic time deserves patience. We're going to understand not just what these objects are, but how we know their ages, why they matter, and what they tell us about the universe's incredible story. We'll explore the methods scientists use to determine ages, from radiometric dating of rocks to analyzing the light from distant galaxies. We'll understand how each discovery fits into the larger picture of cosmic evolution. Throughout this journey, we'll encounter objects and phenomena that challenge our intuition. We'll meet stars so old they formed when the universe was still in its infancy. We'll discover black holes so massive they shouldn't exist according to our current understanding. We'll look at light that has been traveling toward us since before the Earth existed, before the sun formed, before even the Milky Way galaxy took its current shape. So get comfortable. Dim the lights if you want. Maybe make some tea or coffee, because we're going to be here for a while. And let's begin our journey through 13.8 billion years of cosmic history, from the very newest objects in the cosmos to the oldest signals we can detect. Let's start with the babies of the cosmos, the objects that formed so recently that, on cosmic timescales, they might as well have been born yesterday. Right now, at this very moment, stars are being born in our galaxy. Not metaphorically, literally at this second, somewhere in the Milky Way, a cloud of gas is collapsing under its own gravity, heating up, and eventually it will ignite nuclear fusion in its core. A star will be born. The youngest stars we know about are genuinely young. Some are less than 100,000 years old. Now, that might sound like a long time to you. After all, 100,000 years ago, modern humans were just beginning to leave Africa. But in cosmic terms, 100,000 years is nothing. It's a blink. The universe is 13.8 billion years old. A 100,000-year-old star has existed for only 0.001% of cosmic history. Let me put that in perspective. If the universe's entire history were compressed into a single year, with the Big Bang happening at midnight on January 1st, a 100,000-year-old star would have been born at 11:59 p.m. on December 31st. It's that young. Where do we find these cosmic newborns? They're hiding in the stellar nurseries scattered throughout our galaxy. These nurseries are giant clouds of gas and dust called molecular clouds. The most famous one is probably the Orion Nebula, which you can actually see with your naked eye on a clear night. It looks like a fuzzy star in Orion's sword, hanging below his belt. But if you could see it with a telescope, you'd realize it's not a star at all. It's a vast cloud of gas, glowing with the light of newborn stars. The Orion Nebula is about 1,300 light-years away from Earth. That means the light we see from it tonight left there around the year 724. While Charlemagne was consolidating power in Europe, photons were leaving the Orion Nebula, traveling through empty space, and they're just now reaching your eyes. But the Orion Nebula is just one of many stellar nurseries in our galaxy. There's the Eagle Nebula, home to the famous Pillars of Creation photographed by the Hubble Space Telescope. These towering columns of gas and dust are about 6 trillion miles tall, and they're factories for new stars. Inside those pillars, dense knots of gas are collapsing to form protostars. The Pillars of Creation are about 7,000 light-years away. So the image we see today shows them as they were 7,000 years ago, around the time humans were just beginning to develop agriculture and build the first cities. There's also the Carina Nebula, one of the largest star-forming regions in our galaxy, located about 7,500 light-years away in the southern sky. It's home to some of the most massive stars known, including Eta Carinae, a star system so massive and unstable that it could explode as a supernova at any moment. Well, any moment on cosmic timescales. It might have already exploded, and we just haven't seen the light yet. Or it might explode tomorrow. Or it might last another 1,000 years. We don't know. Inside that nebula, stars are forming right now. Well, they were forming 1,300 years ago, which is what we're seeing. The process is actually quite violent. You have these enormous clouds of hydrogen gas mixed with dust floating in space. Most of the time, these clouds are just drifting along, not doing much. But sometimes, something disturbs them. Maybe a nearby star explodes as a supernova, sending a shockwave through the cloud. Maybe two galaxies collide, compressing the gas. Or maybe the cloud just gets massive enough that its own gravity starts to win. These molecular clouds are incredibly cold, usually only about -440 degrees Fahrenheit, just 20 degrees above absolute zero. They're also incredibly diffuse. If you were standing inside a molecular cloud, you probably wouldn't even notice. There might be a few thousand atoms per cubic centimeter, which sounds like a lot until you realize that air on Earth has about 10 to the 19th power atoms per cubic centimeter. That's 10 million trillion atoms. A molecular cloud is a vacuum by Earth standards, but it's dense by the standards of interstellar space. The clouds are massive, though. A typical molecular cloud might contain enough matter to make anywhere from a few hundred to a few million stars. The largest molecular clouds in our galaxy contain enough gas to make tens of millions of sun-like stars. They're the largest structures in the galaxy, apart from the spiral arms themselves. When that happens, the cloud begins to collapse. And here's where it gets interesting. As the cloud collapses, it fragments. It doesn't collapse into one giant ball. Instead, it breaks up into hundreds or thousands of smaller clumps, each one collapsing independently. Each clump will become a star. This fragmentation happens because of instabilities in the gas. As one region starts to collapse faster than its surroundings, it pulls more gas toward itself, which makes it collapse even faster. Meanwhile, other regions are doing the same thing. The result is a cloud that fragments into many separate collapsing regions. As each clump collapses, it heats up. This is basic physics. When you compress a gas, it gets hotter. You experience this every time you pump up a bicycle tire. The pump gets warm because you're compressing air. The same principle applies here, just on a much grander scale. Here's why compression causes heating. In a gas, temperature is really just a measure of how fast the particles are moving. When you compress a gas, you're doing work on it, adding energy to the system. That energy has to go somewhere, and it goes into the motion of the particles. They move faster, which means the temperature rises. In a collapsing protostar, gravity is doing the compression. As the cloud collapses, gravitational potential energy is converted into kinetic energy, the energy of motion. The gas particles move faster and collide more frequently. Each collision generates heat. The center of the collapsing clump, where the density is highest, gets the hottest. The center of each collapsing clump heats up from a few degrees above absolute zero to thousands of degrees, then millions of degrees. The pressure builds and builds, the temperature rises, and when the core reaches about 10 million degrees Fahrenheit, something magical happens. Hydrogen atoms start slamming into each other so hard that they fuse together, creating helium and releasing tremendous amounts of energy. That's nuclear fusion. That's the moment a star is born. But getting there takes time, and it takes mass. A clump needs to be at least about 8% the mass of the Sun to ever get hot enough for hydrogen fusion. Smaller clumps will collapse and heat up, but they'll never reach the critical 10 million degrees. They'll become brown dwarfs, failed stars that glow faintly from leftover heat, but never ignite fusion in their cores. For clumps more massive than that threshold, fusion begins, and the protostar becomes a proper star. The fusion releases enormous amounts of energy, creating an outward pressure that counteracts gravity's inward pull. The star reaches equilibrium, a balance between the crushing force of gravity and the outward pressure from fusion. It settles onto what astronomers call the main sequence, the stable phase of stellar life where it will remain for billions of years. But how do we determine how old a young star or protostar is? It's not like we can cut it open and count rings like a tree. Instead, astronomers use several methods, each with its own strengths and limitations. One method is to look at the star's temperature and luminosity. Young stars are still contracting, and they're brighter and hotter than they will be once they reach the main sequence. By comparing a young star's properties to theoretical models of stellar evolution, astronomers can estimate its age. This method works reasonably well for stars between about 1 million and 100 million years old. Another method is to look at the surrounding environment. If a star is still embedded in its birth cloud, still surrounded by gas and dust, it's probably very young, less than 1 million years old. If it's emerged from the cloud but still close to it, it's probably between 1 million and 10 million years old. If it's far from any molecular clouds, it's probably older. Astronomers also look at the star's rotation. Young stars rotate quickly because they conserved angular momentum as they collapsed. As stars age, they slow down due to magnetic braking, a process where the star's magnetic field interacts with its stellar wind to gradually remove angular momentum. By measuring how fast a star is spinning, astronomers can estimate its age. This method, called gyrochronology, works best for stars between about 100 million and a few billion years old. The youngest stars we've detected are called protostars. They're still in the process of forming. They haven't quite gotten hot enough to start fusing hydrogen yet, but they're on their way. These objects are incredibly difficult to observe because they're still wrapped in the dark clouds of gas and dust they're forming from. Normal visible light can't escape, but they're very hot, so they emit infrared radiation which can penetrate the dust. By using infrared telescopes, astronomers can peer into these stellar nurseries and watch stars being born. One of the youngest protostars ever discovered is called L1527 IRS. That's not a very poetic name, I'll admit. The name comes from the catalogue it was found in and its position in the sky. This protostar is located in the constellation Ophiuchus, about 450 light-years from Earth. How old is L1527 IRS? Astronomers estimate it's between 100,000 and 300,000 years old. It's still gathering mass from the surrounding cloud. It's still heating up. It hasn't even started proper hydrogen fusion yet. In human terms, this isn't even a newborn. This is a baby still in the womb. Studying these young objects teaches us how stars form. And that's crucial, because understanding star formation means understanding galaxy formation, planet formation, and ultimately, understanding how we got here. Every atom in your body was formed inside a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in stellar furnaces billions of years ago. So when we study how stars form, we're studying our own origins. But protostars aren't the only young objects out there. There are also young planets, and studying them gives us insights into how our own solar system formed billions of years ago. In 2008, astronomers discovered a planet orbiting a young star called HR 8799. This planet, called HR 8799b, was significant because it was one of the first planets ever directly imaged around another star. Most planets are discovered indirectly, by watching how they make their parent star wobble, or by watching the star dim when the planet passes in front of it. But HR 8799b was actually photographed. Astronomers used the Gemini Observatory and the Keck Observatory in Hawaii, along with advanced adaptive optic systems that correct for the blurring effects of Earth's atmosphere, to take actual pictures of this planet. The planet is enormous. It's about 7 times more massive than Jupiter, making it a super-Jupiter. And it's young, very young. The star it orbits is only about 30 million years old, which means the planet can't be older than that. 30 million years might sound like a lot, but remember, Earth is 4.5 billion years old. This planet is less than 1% of Earth's age. In human terms, if Earth were a 45-year-old person, HR 8799b would be a 5-month-old baby. 30 million years ago on Earth, it was the Oligocene epoch. The continents were close to their current positions. The climate was cooling after the much warmer Eocene. Primitive primates were scampering through the trees, including early ancestors of modern monkeys and apes. Whales were evolving in the oceans. Grasslands were spreading across continents. And light was leaving HR 8799, beginning its long journey to Earth. What's fascinating about young planets like this is that they're still hot from their formation. When a planet forms, the process generates tremendous heat. All those rocks and dust particles slamming together, the gravitational energy being converted to heat, it makes the newly formed planet glow. Jupiter and Saturn still have heat left over from their formation 4.5 billion years ago. They actually radiate more heat into space than they receive from our space. Jupiter's interior is still gradually contracting and releasing gravitational energy, keeping the planet warmer than it would be from sunlight alone. But HR 8799b is much hotter. It's glowing brightly in the infrared, with a temperature of about 1,600 degrees Fahrenheit. It's still cooling down from the violence of its birth. In a sense, this planet is still an infant, still running a fever from the trauma of being born. The process of planet formation is complex and took scientists many years to understand. It begins with a protoplanetary disk, a flat disk of gas and dust surrounding a newly formed star. This disk is left over from the star formation process. When the cloud collapses to form a star, conservation of angular momentum causes it to spin faster and flatten into a disk. Most of the mass falls into the center to form the star, but a small fraction, about 1%, remains in the disk. In this disk, dust particles collide and stick together. This is the first stage of planet formation, and it happens relatively quickly, in just a few thousand years. The dust grains are tiny, only about a micrometer across, roughly the size of smoke particles. When they collide at low speeds, electrostatic forces cause them to stick together. Over time, these dust grains grow into larger aggregates, then pebbles, then rocks. Once the rocks are about a mile across, gravity becomes important. These mile-sized rocks, called planetesimals, have enough gravity to attract nearby material. They grow faster and faster, sweeping up everything in their orbital path. The largest planetesimals become planetary embryos, objects the size of the Moon or Mars. Finally, the planetary embryos collide and merge, forming full-sized planets. This final stage is violent and chaotic. Giant impacts reshape the growing planets. Earth itself experienced a massive collision with a Mars-sized object called Theia, which created the Moon. The entire process, from dust grains to full-sized planets, takes about 10 million to 100 million years. We found other young planets too, and each discovery helps us understand this process better. In fact, some of the youngest planetary systems we know about are only a few million years old. There's a star called V1298 Tau that's only about 2 million years old. It has planets, though we're still characterizing them. Observing such young systems is like watching planet formation in action. 2 million years. That's incredibly young. To put it in perspective, 2 million years ago on Earth, our ancestor Homo habilis was just evolving in East Africa. Early humans were learning to make stone tools. The first technology, the Pleistocene epoch, was beginning. Africa was populated with megafauna that wouldn't survive to the present day. And this star, V1298 Tau, was just forming, its planets coalescing from the disk of debris around it. Another young system is Beta Pictoris, a star about 20 million years old, located about 63 light-years from Earth. It has a massive debris disk visible in images, and astronomers have discovered at least 2 planets orbiting within that disk. The inner planet, Beta Pictoris b, was discovered in 2008, though it took several years to confirm. It's a massive planet, about 11 times Jupiter's mass, orbiting close enough to its star to complete an orbit in just 20 years. What makes Beta Pictoris particularly interesting is that we can watch the debris disk evolving. The planets are still clearing out their orbital paths, sweeping up leftover material from the planet formation process. The disk is asymmetric, warped by the planet's gravity. It gives us a glimpse of what our own solar system might have looked like 4.6 billion years ago, when Earth and the other planets were still forming and the Sun was surrounded by a similar debris disk. These young stars and planets remind us that the universe isn't static. It's not a museum display frozen in time. It's dynamic, alive, constantly changing. New stars are always forming. New planets are always coalescing. The universe is always being reborn. But if we're talking about the youngest objects in the universe, we need to talk about something even more recent than protostars and young planets. We need to talk about supernovae remnants. When a massive star dies, it doesn't just fade away quietly, it explodes. The explosion is called a supernova, and it's one of the most energetic events in the universe. For a brief moment, a single star can outshine an entire galaxy containing billions of stars. The light from historical supernovae has been recorded by astronomers throughout human history, providing us with detailed records of these cosmic catastrophes. The Chinese recorded a supernova in the year 1054. They called it a guest star, and they described it as being visible even in daylight. That explosion created what we now call the Crab Nebula, and we can still see it today. A glowing cloud of expanding gas about 6,500 light-years away. The Crab Nebula is expanding at about 3 million miles per hour. At its center is a pulsar, a rapidly spinning neutron star that's all that remains of the original massive star. The pulsar rotates 30 times per second, emitting beams of radiation like a cosmic lighthouse. There was another supernova in the year 1572, observed by the Danish astronomer Tycho Brahe. Tycho's supernova, as it's now called, was so bright it was visible in daylight for several weeks. Tycho carefully documented its position and brightness over many months, proving that it was definitely beyond the moon and therefore in the realm of the stars. This was significant because it challenged the prevailing Aristotelian view that the heavens were perfect and unchanging. Here was direct evidence that things in the sky could change dramatically. Another supernova appeared in the year 1604, observed by Johannes Kepler. This was the last supernova seen in our galaxy with the naked eye. Since then, despite our much better telescopes and observing capabilities, we haven't seen another supernova in the Milky Way. Statistically, we're overdue. Supernovae should occur in a galaxy like ours about once every 50 to 100 years. It's been over 400 years since Kepler's supernova. The next one could happen tomorrow, or it could happen in 50 years. We simply don't know. But I want to talk about the absolute youngest supernova remnant we know about in our galaxy. And for that, we need to talk about Cassiopeia A. Cassiopeia A is the remnant of a star that exploded approximately 340 years ago, around the year 1680. Now, you might be wondering why no one recorded it. A supernova should be incredibly bright, visible even in daylight. But here's the interesting thing. Cassiopeia A is about 11,000 light-years away, and between us and it, there's a lot of dust. The dust absorbed most of the light from the supernova. So while the explosion was actually happening around 11,000 years ago, the light reached Earth around 1680, but it was dimmed so much by dust that apparently no one noticed it. Or if they did, they didn't write it down. The astronomer John Flamsteed might have observed it in 1680, marking a 6th magnitude star in that region of sky that was never seen again. But this identification is uncertain. Today, Cassiopeia A is one of the brightest radio sources in the sky. The explosion created a rapidly expanding shell of gas, and that shell is slamming into the surrounding interstellar medium at speeds of about 9 million miles per hour. When gas collides at those speeds, it heats up to millions of degrees and emits X-rays and radio waves. The Chandra X-ray Observatory and other telescopes have studied Cassiopeia A in detail, revealing a complex structure of shells, knots, and filaments. What makes Cassiopeia A special is that it's still young. The explosion happened, from our perspective, only about 340 years ago. The remnant is still expanding, still evolving, still cooling down. Astronomers can actually watch it change from year to year. By comparing images taken decades apart, they can measure how fast different parts of the remnant are expanding. The shell of debris is growing larger. Hot spots are moving. The structure is evolving in real time, on human timescales. This makes Cassiopeia one of the youngest objects in the universe that we can observe. Not the youngest star, not the youngest planet, but the youngest example of stellar death and rebirth. Because that's what supernovae are. They're death and rebirth at the same time. The star dies, but in dying, it seeds the surrounding space with heavy elements. Those elements will eventually form new stars, new planets, maybe even new life. Massive stars create heavy elements through fusion during their lives. In their cores, they fuse hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, and so on up the periodic table. But this process stops at iron. Iron is the most stable nucleus, and fusing iron requires energy rather than releasing it. So once a massive star has built up an iron core, fusion stops. With no more fusion to generate outward pressure, the core collapses catastrophically. The collapse happens in less than a second. The core, about the size of Earth but with more mass than the Sun, collapses to a sphere only about 12 miles across. The density becomes so extreme that protons and electrons are crushed together to form neutrons. The result is a neutron star, where a teaspoon of material would weigh 1 billion tons. But the collapse doesn't stop there smoothly. When the core reaches nuclear density, it suddenly stiffens and the collapse halts. The infalling material bounces off the newly formed neutron star, creating a shockwave that propagates outward through the star. This shockwave rips through the star's outer layers, heating them to billions of degrees. At these extreme temperatures, fusion can occur beyond iron, creating the heaviest elements in the periodic table. Gold, platinum, uranium, all the elements heavier than iron, are created in supernova explosions. The shockwave blasts the star's outer layers into space at speeds of millions of miles per hour. The explosion releases more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. That's the supernova we see, and the expanding debris becomes the supernova remnant. There's an even younger supernova remnant actually, one that we watched form in real time within recent human memory. In February of 1987, a previously unremarkable star in a nearby dwarf galaxy called the Large Magellanic Cloud suddenly exploded. This became known as SN 1987A, and it was the closest supernova observed since 1687, 300 years earlier, long before the invention of modern telescopes. The discovery happened on February 23, 1987. Ian Shelton, a Canadian astronomer working at the Las Campanas Observatory in Chile, was developing photographic plates from the previous night's observations when he noticed a bright star that hadn't been there before. He rushed outside to look at the sky and saw it with his naked eye, a 5th magnitude star where none had existed the night before. Almost simultaneously, astronomers in New Zealand and Australia also noticed the new star. Within hours, telescopes around the southern hemisphere were pointed at it. SN 1987A was visible to the naked eye from the southern hemisphere. Anyone in Australia, South America, or Africa could walk outside on a clear night and see it, a star that had appeared seemingly out of nowhere. At its peak, it reached magnitude 3, easily visible even from light-polluted cities. Astronomers around the world studied it intensely. For the first time in the modern era, we could watch a supernova evolve with sophisticated instruments, from the initial explosion through the gradual fading months later. This supernova was scientifically invaluable. We learned an enormous amount from it. For the first time, we detected neutrinos from a supernova. Neutrinos are nearly massless particles that barely interact with matter. Trillions of them pass through your body every second from the sun, and you never notice. But a supernova produces such an enormous flood of neutrinos that a few can be detected even from halfway across the universe. On February 23, 1987, several neutrino detectors around the world recorded a brief burst of neutrinos lasting just a few seconds. This detection confirmed our theoretical understanding of what happens in a supernova's core. The neutrinos were produced when the star's core collapsed to form a neutron star, and they arrived at Earth about 3 hours before the light did. That's because the neutrinos were produced in the core collapse, while the light was only produced when the shock wave reached the star's surface hours later. Today, more than 37 years after the explosion, the remnant of SN 1987A is still there, still evolving. Astronomers continue to monitor it with the Hubble Space Telescope and other instruments. We're watching as the expanding shell of debris slams into material that the star shed before it exploded. The collision creates bright spots that move and change over the years. It's an unprecedented opportunity to study a supernova remnant from its very beginning. The Large Magellanic Cloud is about 160,000 light-years away. So, the explosion actually happened 160,000 years ago, during the time when early Homo sapiens was spreading across Africa and beginning to develop language and culture. But from our perspective, watching the light arrive in 1987, we're seeing one of the youngest cosmic events observable in real time. At only 37 years old now, SN 1987A is younger than many people reading this description. These are the babies of the universe. Protostars less than a few 100,000 years old, still gathering mass from their birth clouds. Planets only a few million years old, still glowing with formation heat. Supernova remnants a few hundred or a few decades old, still expanding rapidly into surrounding space. They represent the cutting edge of cosmic creation, the newest additions to the universe's vast inventory of objects. But now, let's start moving backward through time. Let's leave the nurseries behind and visit some slightly older objects. Let's talk about our own sun and solar system, which, at 4.6 billion years old, are thoroughly middle-aged by cosmic standards. If stellar lifetimes are analogous to human lifetimes, the sun is in its 40s, a mature, stable star with plenty of life left but past the exuberance of youth. Our sun is a perfectly ordinary star. That's not an insult, it's actually quite remarkable. Out of the hundreds of billions of stars in the Milky Way galaxy, our sun is right in the middle of the pack. Not too big, not too small, not too hot, not too cold, not too young, not too old. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf, though it's actually white when viewed from space. It only appears yellow from Earth's surface because our atmosphere scatters blue light. The sun formed about 4.6 billion years ago. We know this with remarkable precision, and the way we know it is fascinating. We can't directly measure the sun's age, but we can measure the age of the solar system by looking at meteorites. Meteorites are rocks that fall from space and land on Earth. Most of them are fragments of asteroids, and asteroids are leftover debris from the formation of the solar system. They're the building blocks that never got incorporated into planets. When a molecular cloud collapsed 4.6 billion years ago, to form the sun and planets. Not everything ended up in the planets. About 99% of the mass went into the sun, and most of the remaining 1% formed the planets. But a small fraction stayed as asteroids and comets, primitive rocks that have remained essentially unchanged since the solar system's birth. So when we date a meteorite, we're dating the solar system itself. Scientists date rocks using radiometric dating. This technique measures the ratio of radioactive elements to their decay products. For example, uranium slowly decays into lead over billions of years. Uranium comes in several isotopes, but the most common one, uranium-238, has a half-life of about 4.5 billion years. That means if you start with a certain amount of uranium-238, after 4.5 billion years, half of it will have decayed into lead-206. By measuring how much uranium and how much lead are in a rock, and by knowing the rate of decay, you can calculate how old the rock is. But there's a complication. Some lead might have been present when the rock formed, not produced by uranium decay. To account for this, scientists use a clever technique. They measure multiple isotopes of lead and uranium, and by comparing their ratios, they can determine how much lead came from decay versus how much was there originally. The oldest meteorites we've found are called carbonaceous chondrites. These are primitive rocks that have undergone almost no geological processing since they formed. They contain tiny spheres called chondrules, which are droplets of molten rock that formed in the early solar nebula. When scientists date these meteorites using various radioactive isotopes, they consistently get ages around 4.567 billion years. This is the age of the solar system. That's when the sun and planets formed. But let's back up and understand what happened 4.6 billion years ago. There was no star. There was no Earth. There was just a cloud of gas and dust floating in space, part of a larger molecular cloud somewhere in what would eventually become the Milky Way's Orion arm. This cloud contained the remains of previous generations of stars, the heavy elements created in their cores and scattered by supernovae. About 2% of the cloud was these heavy elements. The rest was hydrogen and helium, the primordial elements from the Big Bang. Something disturbed that cloud. Maybe a nearby star went supernova, sending a shock wave through the interstellar medium. The shock wave compressed the cloud, and once compressed, gravity took over. The cloud began to collapse. Maybe the supernova that triggered the collapse was the same one that created the heavy elements in the cloud. Or maybe it was a more recent explosion, and the cloud had been enriched by multiple previous supernovae. We don't know for certain. As it collapsed, the cloud started to spin. This is conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in. The cloud spun faster and faster as it contracted. And as it spun, it flattened out into a disk. Think of spinning pizza dough. As you spin it, centrifugal force flattens it into a circular disk. The same thing happened here. Most of the mass, about 99%, fell into the center, forming our star. The rest stayed in the disk, forming what's called a protoplanetary disk. This disk was about 100 astronomical units across, where 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the disk extended about 9 billion miles from the newborn star. The temperature in the disk varied dramatically. Close to the Sun, it was hot, around 2000 degrees Fahrenheit. Far from the Sun, it was cold, approaching -400 degrees. This temperature gradient determined what kinds of materials could condense at different distances. Close to the Sun, only materials with high melting points could form solid particles. These were metals and silicates, rocky materials. Farther out, beyond what's called the frost line at about 2.7 astronomical units, water could freeze into ice. Even farther out, gases like methane and ammonia could condense. This is why the inner solar system has rocky planets, and the outer solar system has gas giants. The rocky planets Mercury, Venus, Earth, and Mars formed from metal and rock in the hot inner disk. The gas giants, Jupiter, Saturn, Uranus, and Neptune, formed beyond the frost line where ices could exist, allowing them to accumulate much more mass. But about 1% of the mass stayed in the disk, and that's where the planets formed. Dust particles in the disk started to stick together. Little pebbles became bigger rocks became boulders, boulders became planetesimals, objects the size of mountains. And planetesimals collided and merged, growing larger and larger, until finally they became planets. The whole process took about 10 to 100 million years. That's fast on cosmic timescales. In the grand scheme of things, the solar system assembled itself quite quickly. The Sun reached the main sequence, beginning stable hydrogen fusion after about 50 million years. The terrestrial planets finished forming after about 100 million years. The gas giants probably formed even faster, within 10 million years, before the gas in the protoplanetary disk was blown away by the young sun's intense radiation and solar wind. Earth formed about 4.54 billion years ago. We know this from dating the oldest rocks on Earth and the oldest moon rocks brought back by the Apollo astronauts. The oldest Earth rocks are found in Western Australia, in a region called the Jack Hills. These rocks contain mineral grains called zircons, which are incredibly resistant to weathering and can survive when the rest of the rock has been altered. The oldest zircons are 4.4 billion years old, telling us that Earth's crust had already solidified by that time. But Earth itself is older than its oldest surviving rocks. The planet underwent a period of intense bombardment after it formed, with impacts melting and reworking the surface repeatedly. Most of the original crust was destroyed and recycled back into the mantle. The oldest rocks we find today are from a later period when Earth had cooled enough for a permanent crust to form. The Moon itself formed from a giant impact. Early in Earth's history, about 50 million years after the planet formed, a Mars-sized object called Theia slammed into Earth. This wasn't a glancing blow. It was a direct, catastrophic collision. The impact was so violent that it vaporized Theia and a large chunk of Earth's mantle. Both bodies were completely disrupted. For a brief time, Earth wasn't even a solid planet. It was a cloud of vaporized rock. The debris from the impact went into orbit around Earth. Over time, this debris coalesced into the Moon. Computer simulations of this giant impact can reproduce many of the Moon's properties: its size, its orbit, its composition. The Moon is made of the same material as Earth's mantle, because it formed from mantle material blasted into space by the collision. That happened about 4.5 billion years ago, give or take 50 million years. So the Moon is roughly the same age as Earth. In fact, by dating moon rocks, we can constrain the timing of the giant impact. The oldest moon rocks are about 4.46 billion years old, consistent with the Moon forming shortly after Earth. Now, 4.6 billion years is a long time. But it's not that long compared to the age of the universe. The universe is 13.8 billion years old. The Sun is 1/3 that age. If the universe were a 40-year-old person, the Sun would be about 13 years old, a teenager. And here's something interesting. The Sun is a third-generation star, Let me explain what that means. The very first stars in the universe, the ones that formed a few 100 million years after the Big Bang, were made almost entirely of hydrogen and helium. That's because hydrogen and helium were the only elements created in the Big Bang. Everything else, all the heavier elements like carbon, nitrogen, oxygen, iron, were created later inside stars. Those first stars lived, fused hydrogen into helium, helium into carbon, carbon into heavier elements, and then they exploded as supernovae, scattering those heavy elements into space. The second generation of stars formed from gas clouds that included those heavy elements. They lived, created even more heavy elements, and exploded. And finally, the third generation of stars, like our Sun, formed from gas that had been enriched with heavy elements from two previous generations of stars. We know the Sun is a third-generation star because of its composition. About 2% of the Sun's mass is elements heavier than hydrogen and helium. Astronomers call these heavy elements metals, which is confusing because it includes things like oxygen and carbon that you wouldn't normally think of as metals. But in astronomy, anything heavier than helium is a metal. That 2% might not sound like much, but it's crucial. Without those heavy elements, planets like Earth couldn't exist. Rocky planets are made of metals and silicates. If the Sun had formed from pristine Big Bang gas, with no heavy elements, there would be no Earth, no rocks, no life. So, the Sun's age, 4.6 billion years, places it firmly in the middle chapter of the universe's story. It's not a first-generation star from the early universe. It's not a recently formed star from a modern stellar nursery. It's middle-aged, third generation, ordinary in every way except that it happens to host a planet with life. Let's zoom out now and look at other stars in our cosmic neighborhood. The Milky Way contains stars of all ages. Some are younger than our star, some are older. The mix tells us about the galaxy's history. Most of the stars you can see with your naked eye are actually younger than to a star. That's not because young stars are more common, it's because young stars are often more luminous. They burn brighter. So even though they're farther away, we can see them. Take Sirius, the brightest star in the night sky. Sirius is actually a binary system, two stars orbiting each other. The main star, Sirius A, is only about 240 million years old. That's quite young. 240 million years ago on Earth, it was the Triassic period. Dinosaurs were just beginning to evolve. The supercontinent Pangaea was starting to break apart. Sirius is 8.6 light-years away, which makes it one of our nearest neighbors, and it's a young neighbor, still in its energetic youth, burning through its hydrogen fuel at a prodigious rate. On the other hand, some nearby stars are much older. Captain's star, named after the Dutch astronomer who discovered its high speed through space, is about 11 billion years old. That's more than twice the age of our star. Captain's star formed when the universe was less than 3 billion years old, in the very early days of galaxy formation. Captain's star is only about 13 light-years away. So we have this interesting situation where we're sandwiched between very young stars and very ancient ones. The Milky Way is a multi-generational neighborhood, with stars from different epochs all mixed together. But as we move through this journey from young to old, we should probably take a moment to appreciate the Sun's future, because it tells us something about stellar evolution. The Sun is currently in what astronomers call the main sequence. That's the stable phase of a star's life when it's fusing hydrogen into helium in its core. The Sun has been doing this for 4.6 billion years, and it will continue for another 5 billion years or so. then things will change dramatically. When the sun runs out of hydrogen in its core, the core will start to collapse and heat up. The extra heat will cause the outer layers to expand enormously. The sun will become a red giant, swelling up to perhaps the orbit of Mars. It will engulf Mercury and Venus. Earth might survive, or it might not. But even if Earth survives, it won't be habitable. The heat will boil away the oceans and scorch the surface. This will happen in about 5 billion years. Then, after another billion years or so, the sun will shed its outer layers, creating a beautiful planetary nebula, and the core will collapse into a white dwarf, a dense ember about the size of Earth, but with half the sun's current mass. The white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark sphere of degenerate matter floating through space. But that's billions of years in the future. Right now, the sun is stable, reliable, steadily converting hydrogen to helium, providing the energy that makes life on Earth possible. As we continue our journey through cosmic time, we need to leave the solar system behind and venture deeper into the galaxy. We need to find stars older than the sun, older than Kapteyn's star, stars that formed in the earliest days of the Milky Way. The oldest stars in the Milky Way are found in the galactic halo and in globular clusters. These stars formed over 10 billion years ago, some as old as 13 billion years. They're witnesses to the galaxy's youth, fossil records of a time when the Milky Way was just beginning to take shape. Globular clusters are dense, spherical collections of stars, and they're among the most beautiful objects you can observe through a telescope. They contain anywhere from tens of thousands to millions of stars, all packed into a relatively small volume, typically only about 100 light-years across. The stars in a globular cluster all formed around the same time from the same gas cloud, so they're all roughly the same age. When you look at a globular cluster through a telescope, you're seeing hundreds of thousands of stars that were all born together billions of years ago. The Milky Way has about 150 known globular clusters, though there may be more hiding behind the dust and gas of the galactic disk. They orbit in the galactic halo, the spherical region surrounding the flat disk of the galaxy. Their orbits are different from the orderly, circular orbits of stars in the disk. Globular clusters have elliptical, often highly inclined orbits that can take them far above and below the galactic plane. Some clusters plunge right through the disk, while others stay high in the halo, never approaching the galactic center. Some of these globular clusters are incredibly old. Take M92, also known as NGC 6341. It's a globular cluster in the constellation Hercules, about 27,000 light-years from Earth. M92 contains several 100,000 stars, and those stars are about 13.2 billion years old. 13.2 billion years. That's almost as old as the universe itself. The universe is 13.8 billion years old, so M92 formed only about 600 million years after the Big Bang. To put that in perspective, 600 million years is less than 5% of the universe's current age. Think about that. When these stars formed, the universe was barely out of its infancy. What was the universe like 13.2 billion years ago? It was much smaller, much denser, much hotter than it is today. Galaxies were just beginning to form from the collapse of dark matter halos. The first generation of stars had already lived and died, enriching the cosmos with heavy elements. But galaxy formation was still in its early stages. The Milky Way as we know it didn't exist yet. It was just beginning to assemble from smaller proto-galaxies merging together. And in that ancient cosmos, a cloud of gas collapsed, and hundreds of thousands of stars formed nearly simultaneously. They've been orbiting around what would become the Milky Way ever since. A tight cluster of ancient stars, gravitationally bound together, slowly orbiting through the galactic halo. Over billions of years, the cluster has passed through the galactic disk dozens of times, each passage stirring up its structure slightly, but it's remained intact. These ancient stars still bound together after 13 billion years. The individual stars in M92 are called population 2 stars. That's astronomical terminology for old stars with low metal content. Remember, in astronomy, metals are any elements heavier than hydrogen and helium. The very first stars in the universe had no metals at all. They were pure hydrogen and helium, formed from the primordial gas created in the Big Bang. Those are called population 3 stars, and we've never actually observed one. They all died long ago. But population 2 stars formed from gas that had been slightly enriched by that first generation. They have some metals, but not much. Maybe 0.1% heavy elements compared to the Sun's 2%. Those population 2 stars are what we find in globular clusters like M92. Their low metal content is a signature of their ancient origins, formed from gas that had only been slightly processed by previous stellar generations. These ancient stars are different from the Sun in other ways too. They're smaller, dimmer, and cooler. The brightest stars in M92 are red giants, stars that have exhausted the hydrogen in their cores and expanded to hundreds of times their original size. But most of the stars are red dwarfs, small cool stars with masses less than half the Sun's mass. And here's what's remarkable. Those red dwarfs are still alive after 13 billion years. They're still fusing hydrogen into helium in their cores. They'll continue to do so for tens of billions of years more, possibly even hundreds of billions of years. That's because small stars burn their fuel very slowly. A red dwarf, with 1/10 the Sun's mass, will live for several trillion years, far longer than the current age of the universe. So some of the stars in M92 will still be shining long after the Sun has died. The Sun will exhaust its hydrogen in about 5 billion years, expand into a red giant, and eventually shed its outer layers to become a white dwarf. But the smallest stars in M92 will still be on the main sequence, steadily fusing hydrogen, barely changed from how they are today. Think about that for a moment. These stars have been burning for 13.2 billion years. They existed before the Earth, before the solar system, before the Milky Way's spiral arms formed. They've witnessed nearly the entire history of the universe, and they'll continue burning for billions of years to come, outlasting almost every other star in existence. Other globular clusters in the Milky Way are similarly ancient. M15, M30, NGC 6752 all contain stars over 12 billion years old. By studying these clusters, astronomers can learn about the early universe, about the first episodes of star formation, about the chemical composition of gas in the early cosmos. We can also study individual ancient stars scattered through the galaxy. These are stars that might have formed in globular clusters that have since been disrupted, or they might have formed in small dwarf galaxies that merged with the Milky Way billions of years ago. Finding and studying these stars is like doing archaeology, piecing together the Milky Way's formation history from the ancient relics that survive to the present day. But even these ancient globular clusters aren't the oldest stars we've found. There are individual stars scattered through the Milky Way that are even older, stars that have survived since the very earliest days of galaxy formation. One of the most famous is HD 140283, affectionately nicknamed the Methuselah Star, after the biblical figure who lived 969 years. That's not a very memorable scientific name, but this star is remarkable. It's located about 190 light-years from Earth in the constellation Libra, and it's about 13.5 billion years old. 13.5 billion years. That's only 300 million years younger than the universe itself. When this star formed, the universe was still in its infancy, barely emerging from the cosmic dark ages when the first stars and galaxies were just beginning to light up the cosmos. HD 140283 is called a population 2 star, like those in globular clusters. But what makes it special is its extremely low metal content. It has about 1/1,000,000th the metal content of our star. Let me repeat that. 1/1,000,000th. That's an almost incomprehensibly small amount. It means this star formed from gas that had barely been enriched by previous stars. It's almost a population 3 star, almost first generation, but not quite. The fact that it has any metals at all tells us there must have been at least one previous generation of stars that lived, created heavy elements through fusion, and then died, scattering those elements into space. HD 140283 formed from gas that included a tiny amount of that enriched material. It's a second-generation star, but barely. It's one of the oldest stars we've ever found. Astronomers discovered HD 140283 in 2007, but they didn't realize how old it was at first. The star had been catalogued years earlier as part of a survey of nearby stars, but no one had analyzed its composition in detail. It took careful spectroscopic analysis to measure its metal content and determine its age. Spectroscopy is one of the most powerful tools in astronomy. It involves splitting a star's light into its component colors, like a prism splitting sunlight into a rainbow. But unlike a simple rainbow, a stellar spectrum contains thousands of dark lines. These are absorption lines, places where atoms in the star's atmosphere have absorbed specific wavelengths of light. Each element produces its own unique pattern of absorption lines, like a fingerprint. By studying these lines, astronomers can determine what elements are present in the star and in what quantities. When astronomers analyzed the spectrum of HD 140283, they found almost no metal absorption lines. The hydrogen and helium lines were strong, as expected, but the lines from heavier elements were incredibly weak. This indicated an extremely low metal content, which in turn indicated an extremely old age. Stars with low metal content formed from gas that hadn't been enriched much by previous generations, which means they formed early in cosmic history. But determining the exact age required sophisticated stellar models. Astronomers used computer simulations that track how stars evolve over time, how their temperature and brightness change as they age, how their chemical composition affects their evolution. By comparing HD 140283's observed properties to these models, they estimated its age at 13.5 billion years, plus or minus a few 100 million years. There was initially some controversy about this age. 13.5 billion years is very close to the age of the universe itself, 13.8 billion years. If the star were older than the universe, that would be a problem. It would mean either our age for the universe was wrong, or our age for the star was wrong, or we fundamentally misunderstood something about stellar evolution or cosmology. But careful reanalysis of the data, using improved measurements and better models, confirmed that the star is indeed about 13.5 billion years old, comfortably younger than the universe. The margins of error on both measurements allow them to be consistent. The universe is 13.8 billion years old, with an uncertainty of about 30 million years. The star is 13.5 billion years old, with an uncertainty of a few hundred million years. There's no contradiction. What's fascinating is imagining what this star has witnessed. When HD 140283 formed, the universe was only 300 million years old. There were no galaxies yet, not in the modern sense. The first galaxies were just beginning to coalesce from the dark matter structures that had formed after the Big Bang. These proto-galaxies were small, irregular, chaotic, nothing like the grand spiral and elliptical galaxies we see today. The cosmic microwave background, the afterglow of the Big Bang, was still much hotter and brighter than it is today. It filled space with infrared radiation, warming the early universe slightly. The first quasars were just turning on, powered by supermassive black holes that had somehow grown to enormous sizes in a remarkably short time. And this star has been here, steadily burning hydrogen into helium since that ancient time. It's traveled billions of light years as the universe expanded. It's watched galaxies form and evolve. It's seen countless other stars born and die around it. It's survived multiple close encounters with other stars, multiple passages through the Milky Way's disk where tidal forces could have disrupted it. And it's still here, still shining, a faint red spark in the night sky, visible through a modest telescope. The star is small and dim, only about 80% the mass of the Sun, and it's only 17% as luminous. It's a red dwarf, though actually it's evolved slightly beyond that stage and is now what's called a subgiant, beginning to exhaust the hydrogen in its core. But it's still a small, cool star that will burn for tens of billions of years, possibly even longer than the current age of the universe. There are other extremely old stars scattered through the galaxy. Astronomers have found stars that are 13.5, even approaching 13.7 billion years old. Each discovery helps us understand the early universe, the first episodes of star formation, the chemical evolution of galaxies. These are the elders of the cosmos, the survivors from the universe's youth, living fossils that have endured for almost the entire history of time. But here's an interesting puzzle. How can we have stars that are almost as old as the universe itself? There's only a few hundred million years between the Big Bang and the formation of these ancient stars. What happened in that brief window of time? To understand that, we need to talk about the dark ages of the universe. And no, that's not a reference to medieval history. It's a reference to the period between the Big Bang and the formation of the first stars. After the Big Bang, the universe was a hot, dense soup of particles. It was opaque, meaning light couldn't travel through it. Photons would be absorbed and re-emitted constantly, unable to move freely. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, it cooled enough that electrons combined with protons to form neutral hydrogen atoms. This moment is called recombination, and it marked the moment when the universe became transparent. Photons could finally travel freely. Those photons are still traveling today. We detect them as the cosmic microwave background, the afterglow of the Big Bang. We'll talk more about that later, because it's one of the oldest things we can observe. But after recombination, the universe entered the Dark Ages. This is a period lasting from about 380,000 years after the Big Bang to about 150 million years after the Big Bang. During this time, the universe was filled with neutral hydrogen gas, but there were no stars yet. No galaxies, no light sources, just dark clouds of hydrogen floating in expanding space. Eventually, though, gravity started to do its work. Small density fluctuations in the hydrogen gas, fluctuations that had been imprinted during inflation in the first fraction of a second after the Big Bang, started to grow. Denser regions attracted more matter. Over millions of years, these regions grew denser and denser. Eventually, the first stars ignited. These are the population 3 stars we talked about earlier, the ones made of pure hydrogen and helium. They formed about 150 to 200 million years after the Big Bang. These first stars were different from modern stars. Without any metals in their composition, they could grow much larger. Some of them might have been hundreds of times more massive than our star, and they burned hot and fast. A star, hundreds of times the sun's mass, might live for only a few million years before exploding as a supernova. Those explosions enriched the surrounding space with heavy elements, the first metals in the universe. And from that enriched gas, the second generation of stars formed, population 2 stars, like those we find in ancient globular clusters and old stars like HD 140283. We've never actually observed a population 3 star. They all died billions of years ago. But astronomers are actively searching for them using the most powerful telescopes we have. The James Webb Space Telescope, launched in December of 2021, is designed to look at the very distant, very early universe, and one of its goals is to detect the first galaxies and possibly even the first stars. Distance and time are linked in astronomy. When we look at a galaxy 1 billion light years away, we're seeing it as it was 1 billion years ago. The light we see left that galaxy 1 billion years ago and has been traveling toward us ever since. So if we want to see the early universe, we need to look at very distant objects. The James Webb Space Telescope has already found some of the most distant galaxies ever observed, galaxies that existed when the universe was only a few 100 million years old. These galaxies contain population 2 stars, second-generation stars formed from gas enriched by the first stars. But we haven't found population 3 stars yet. They might be out there, in even more distant, even earlier galaxies. Or they might be impossible to detect with current technology because they're so far away, their light so redshifted and faint. But even if we never directly observe a population 3 star, we know they existed. We see their legacy in the composition of population 2 stars. We see it in the heavy elements scattered throughout the universe. The first stars lived, enriched the cosmos, and died, paving the way for everything that came after. This brings us to an important milestone in our journey from young to old. We've now reached the edge of what we can observe directly as stars. The oldest stars we can see are about 13.5 billion years old, formed just a few 100 million years after the Big Bang. But there are even older structures in the universe, structures that formed before the first stars. To find them, we need to look at galaxies. Galaxies are vast collections of stars, gas, dust, and dark matter, all bound together by gravity. The Milky Way is a galaxy containing a few 100 billion stars, but there are billions of galaxies in the observable universe, each containing billions or even trillions of stars. Some galaxies are young, still actively forming stars. Others are old and quiet, having exhausted their gas supply long ago. And a few are incredibly ancient, formed when the universe was still in its infancy. The oldest galaxies we've discovered are truly ancient. They existed when the universe was less than 500 million years old. That's only about 3.5% of the universe's current age. In July of 2023, astronomers using the James Webb Space Telescope announced the discovery of a galaxy called JADE SGS Z13-0. The name is a mouthful, but what matters is its age. This galaxy existed when the universe was only about 330 million years old. 330 million years after the Big Bang. That's incredibly early. Think about what that means. The universe had just emerged from the Dark Ages. The first stars had only recently formed, and already galaxies were assembling. JADESGS Z13-0 is about 13.5 billion light-years away. That's a mind-boggling distance. The light we're seeing from it left when the universe was only 330 million years old and has been traveling through space ever since. It's passed through the expanding universe, been stretched by the expansion, redshifted from ultraviolet light to infrared light. And finally, after more than 13 billion years, it's reached our telescopes. What does JADESGS-Z13-0 look like? We don't have a detailed picture. It appears as a small red smudge in Webb's images. Red because its light has been redshifted so much by the universe's expansion. But even from that small smudge, we can learn a lot. We can measure the galaxy's distance using redshift. Redshift is the stretching of light waves caused by the expansion of space. The more space has expanded between the galaxy and us, the more redshifted the light is. By measuring the redshift, we can calculate how far away the galaxy is and when the light was emitted. We can also measure the galaxy's properties. JADESGS-Z13-0 is small, only a few 100 million times the mass of the Sun in stars. That's tiny compared to the Milky Way, which is hundreds of billions of solar masses. But remember, this galaxy is very young. It's still forming. Over the next billions of years, it would have grown much larger, merging with other galaxies, accumulating more mass, possibly becoming a massive galaxy like the Milky Way. Or maybe it didn't survive. Maybe it was torn apart in a merger. Maybe it merged with other galaxies and lost its identity. We can't know because we're seeing it as it was 13.5 billion years ago. Its light is only just now reaching us. By the time we're seeing it, it's already long gone, transformed into something else or destroyed entirely. But the fact that it existed at all is remarkable. 330 million years after the Big Bang, and galaxies were already forming. That's much faster than astronomers expected. Early models of galaxy formation suggested it should take longer for galaxies to assemble, but observations keep finding earlier and earlier galaxies, pushing back the timeline of cosmic structure formation. Another incredibly ancient galaxy is GNZ11. This galaxy was discovered in 2016 using the Hubble Space Telescope and later studied in more detail by James Webb. GNZ11 existed when the universe was about 400 million years old. What makes GNZ11 interesting is that it's actively forming stars at a furious rate. It's producing new stars at about 20 times the rate of a typical galaxy today. It's also quite bright, which is surprising for such an early galaxy. The brightness suggests it might contain massive stars, possibly even some of the last surviving population 3 stars, though that's still speculative. These ancient galaxies give us a window into the early universe. They show us what the cosmos was like when it was young, when structure was just beginning to form, when the first galaxies were assembling from primordial clouds of gas. But galaxies themselves aren't the oldest structures we can observe. There's something even older, something that formed even earlier in cosmic history. To find it, we need to talk about quasars. Quasars are some of the most luminous objects in the universe. A single quasar can outshine an entire galaxy, radiating more energy than trillions of stars. They're visible across billions of light years, beacons shining from the distant past. We now know that quasars are powered by supermassive black holes at the centers of galaxies. Material falling into the black hole heats up to millions of degrees and emits tremendous amounts of radiation. The black hole itself doesn't emit light, but the swirling disk of matter around it, called an accretion disk, shines brilliantly. The most distant quasars we've discovered are incredibly old. They existed when the universe was less than 1 billion years old. And here's what's puzzling. These quasars contain supermassive black holes that are billions of times the mass of our star. How did black holes get so massive so quickly? Let's back up and talk about black hole formation. Stellar mass black holes form when massive stars collapse at the end of their lives. A star 20 times the mass of the Sun will end its life in a supernova, and its core will collapse into a black hole maybe 10 times the mass of our Sun. But supermassive black holes are millions or billions of solar masses. They can't form from a single star collapse. Instead, they must have grown over time, either by merging with other black holes or by accreting gas and stars from their surroundings. The problem is, this growth takes time, a lot of time. Current models suggest it should take billions of years for a black hole to grow from stellar mass to supermassive. But we're finding supermassive black holes that existed when the universe was less than 1 billion years old. There simply wasn't enough time for them to grow using conventional mechanisms. This is one of the major puzzles in modern astronomy. How did supermassive black holes form so early in cosmic history? One possibility is that they didn't start from stellar mass black holes. Maybe they started much larger. There are theoretical objects called direct collapse black holes, which could have formed when massive clouds of gas collapsed directly into black holes without ever forming stars. These direct collapse black holes might have been thousands or tens of thousands of solar masses right from the start, giving them a head start on growth. Another possibility is that the early universe had conditions that allowed black holes to grow faster than we think. Maybe the gas density was higher, allowing for more rapid accretion. Maybe black holes merged more frequently in the crowded early universe. We don't know the answer yet. It's an active area of research. But what we do know is that supermassive black holes existed very early, and the quasars they powered are among the oldest objects we can observe. The most distant quasar ever discovered is called J0313-1806. It's a cumbersome name, derived from its coordinates on the sky. This quasar existed when the universe was only 670 million years old. 670 million years after the Big Bang. That's less than 5% of the universe's current age. And this quasar contains a supermassive black hole about 800 million times the mass of our Sun. 800 million solar masses. And the universe is less than 700 million years old. It's astounding. The light from J0313-1806 has been traveling toward us for over 13 billion years. It's been stretched by the expansion of the universe, redshifted from optical and ultraviolet wavelengths into the infrared. By the time it reaches our telescopes, it's faint and red, but it's detectable. What was the universe like when this quasar was shining? It was still in the epoch of reionization, a period when the first stars and galaxies were ionizing the neutral hydrogen that filled space. The universe was transforming from a dark, neutral state to a transparent, ionized state. Quasars, like J0313-1806, contributed to that transformation, their intense radiation ionizing vast bubbles of space around them. This quasar, and others like it, also tell us about galaxy formation. Because quasars are powered by supermassive black holes, and supermassive black holes live at the centers of galaxies, every quasar represents a galaxy. The galaxy around J0313-1806 would have been forming stars, growing, evolving. We can't see the galaxy directly because the quasar is so bright it overwhelms the light from the stars. But we know it's there. Finding these early quasars is challenging. They're rare and faint. Astronomers have to survey huge areas of sky to find them. But every discovery pushes back our understanding of when structure formed in the universe. Every new quasar tells us something about the conditions in the early cosmos. As we continue our journey through cosmic time, we're now approaching the limits of what we can observe with current technology. We've found stars that are 13.5 billion years old, galaxies that formed 300 million years after the Big Bang. Quasars, powered by supermassive black holes that existed less than 700 million years after the Big Bang. But there's still more. There are structures even older, relics from a time before stars, before galaxies, before any objects as we know them. To find them, we need to look at the structure of the universe itself. We need to talk about the cosmic web and the distribution of dark matter. If you could zoom out and look at the universe on the largest scales, you'd see that it's not uniformly distributed. Galaxies aren't randomly scattered through space. Instead, they're arranged in a vast cosmic web, a network of filaments and sheets surrounding enormous voids. This structure is called the cosmic web, and it's one of the most beautiful patterns in nature. Galaxies are concentrated along the filaments, like beads on a string. The filaments intersect at nodes, where you find massive galaxy clusters. Between the filaments are vast, empty regions called voids, where very few galaxies exist. The cosmic web is shaped by dark matter. Dark matter is a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it directly, but we know it exists because of its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. Galaxy clusters hold together more tightly than the visible matter can explain, and the cosmic web structure itself requires dark matter to form. About 85% of the matter in the universe is dark matter. Only 15% is the ordinary matter that makes up stars, planets, gas, dust, and us. Dark matter dominates the gravitational landscape of the universe. The cosmic web we see today, with its filaments and voids, has been growing since very early times. Shortly after the Big Bang, the universe was nearly uniform. But there were tiny density fluctuations, tiny regions that were slightly denser or slightly less dense than average. These fluctuations were imprinted during inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. Over time, gravity amplified those tiny fluctuations. Denser regions attracted more matter and became denser still. Less dense regions lost matter and became voids. By a few 100 million years after the Big Bang, dark matter had collapsed into structures called dark matter halos. Dark matter halos are concentrations of dark matter held together by their own gravity. They range in size from small halos that might host a single galaxy to enormous halos that host galaxy clusters. The Milky Way sits inside a dark matter halo that's probably about 10 times more massive than all the visible matter in the galaxy. These dark matter halos formed before galaxies. In fact, galaxies formed inside dark matter halos. The dark matter provided the gravitational wells that gas could fall into. The gas collected in the centers of the halos, cooled, and formed stars. And thus, galaxies were born. The oldest dark matter structures in the universe formed about 100 million years after the Big Bang. That's before the first stars. These were small halos, the seeds that would eventually grow into larger structures. By 200 million years after the Big Bang, dark matter halos were large enough to host the first galaxies. So when we look at ancient galaxies like JADES GSZ 130, we're seeing visible matter inside dark matter halos that are slightly older. The halo formed first, the galaxy formed inside it. The halo itself is invisible, but we can infer its presence from the galaxy's motion and the way light bends around it through gravitational lensing. These ancient dark matter structures are, in a sense, the oldest structures in the universe that we can study indirectly. We can't see dark matter, but we can see its effects. We can map the cosmic web by observing how galaxies are distributed. We can infer the presence of dark matter halos by watching how galaxies move. We can detect dark matter's gravitational influence on light through lensing. And when we do all of that, we're seeing structures that formed in the very early universe, in the first few 100 million years after the Big Bang. These are the scaffolds upon which everything else was built. The cosmic web of dark matter shaped where galaxies formed. It shaped where stars formed. It shaped where planets formed. It shaped where we are. But as ancient as dark matter structures are, there's still something older. There's a signal from even earlier in cosmic history, a faint echo from a time before any structures existed at all. To hear that echo, we need to talk about the cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light in the universe. It's a faint glow of radiation that fills all of space, coming from every direction. It's the afterglow of the Big Bang, the remnant heat from the universe's birth. The CMB was created 380,000 years after the Big Bang, during the moment of recombination when the universe became transparent. Before that, the universe was opaque, a hot plasma of electrons and protons. Photons couldn't travel freely. They'd be absorbed and re-emitted constantly, scattering off the free electrons. But when the universe cooled to about 3,000 degrees Fahrenheit, electrons and protons combined to form neutral hydrogen atoms. Without free electrons to scatter off of, photons could suddenly travel freely. The universe became transparent, and those photons have been traveling through space ever since. We detect those photons today as the cosmic microwave background. The light has been stretched by the expansion of the universe, redshifted from visible and infrared light all the way down to microwave wavelengths. The CMB today has a temperature of about -455 degrees Fahrenheit, just 2.7 degrees above absolute zero. The cosmic microwave background was predicted in the 1940s by George Gamow and others as a consequence of the Big Bang theory. If the universe started in a hot, dense state and has been expanding and cooling ever since, there should be leftover radiation from that early hot phase. And in 1964, Arno Penzias and Robert Wilson accidentally discovered it. Penzias and Wilson were radio astronomers working at Bell Labs in New Jersey. They were testing a sensitive antenna designed for satellite communication when they noticed a persistent background noise. No matter which way they pointed the antenna, The noise was there. They tried everything to eliminate it. They even cleaned pigeon droppings out of the antenna, thinking that might be the source. But the noise remained. Eventually, they realized they were detecting radiation from space, and after consulting with theoretical physicists, they understood what they'd found. It was the cosmic microwave background, the afterglow of the Big Bang. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery. Since then, the CMB has been studied in incredible detail. In 1989, NASA launched the Cosmic Background Explorer, or COBE, satellite to map the CMB across the entire sky. COBE found that the CMB is remarkably uniform. Its temperature is the same in all directions, to within 1 part in 100,000. But it's not perfectly uniform. There are tiny variations, tiny hot and cold spots. These variations are incredibly important. They're the imprints of the density fluctuations that existed 380,000 years after the Big Bang. The slightly denser regions appear as slightly warmer spots in the CMB. The slightly less dense regions appear as slightly cooler spots. Those tiny fluctuations are the seeds that grew into all the structure we see today. The cosmic web, the galaxies, the stars, us, everything traces back to those tiny variations in the density of the early universe. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, to map the CMB in even more detail. And in 2009, the European Space Agency launched the Planck satellite, which produced the most detailed map of the CMB we have. Looking at a map of the CMB is like looking at a baby picture of the universe. It shows us what the cosmos looked like 380,000 years after the Big Bang, before any stars or galaxies existed. It's the oldest snapshot we have. The CMB is 13.8 billion years old, minus 380,000 years. It's older than any star, any galaxy, any structure. It's a direct signal from the early universe, a message sent across more than 13 billion years of cosmic history. What can we learn from the CMB? A tremendous amount. By analyzing the pattern of hot and cold spots, astronomers can measure fundamental properties of the universe. We can determine the age of the universe, the expansion rate, the curvature of space, the density of matter and dark matter, and the density of dark energy. The CMB tells us that the universe is flat, meaning its overall geometry is Euclidean. It tells us that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. It tells us that the universe is 13.8 billion years old. The CMB also tells us about inflation, that brief period of exponential expansion in the first tiny fraction of a second after the Big Bang. The quantum fluctuations generated during inflation were stretched to cosmic scales, and they became the density fluctuations we see imprinted in the CMB. By studying the CMB, we're learning about events that happened 10 to the minus 35 seconds after the Big Bang. That's a decimal point, followed by 34 zeros and then a 1. That's an almost incomprehensibly short time. But the evidence of what happened then is still visible in the sky today, encoded in the pattern of the cosmic microwave background. So the CMB, formed 380,000 years after the Big Bang, is the oldest light we can see. It's the oldest direct signal from the early universe. But is it the oldest thing we can study? Not quite. There's one more phenomenon we need to discuss, one more relic from even earlier times, and that's gravitational waves from the Big Bang. Gravitational waves are ripples in space-time itself, created when massive objects accelerate. Einstein predicted their existence in 1916 as a consequence of general relativity, but they weren't detected until 2015. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves from two black holes colliding about 1.3 billion light-years away. The collision sent ripples through space-time that spread outward at the speed of light. When those ripples reached Earth, they stretched and compressed space by an incredibly tiny amount, less than 1,000th the width of a proton. But LIGO's detectors were sensitive enough to measure that tiny distortion. Since then, LIGO and other gravitational wave detectors have observed dozens of events, mostly colliding black holes and neutron stars. But there's another source of gravitational waves that astronomers are desperately trying to detect: waves from the Big Bang itself. During inflation, that brief period of exponential expansion in the first fraction of a second after the Big Bang, quantum fluctuations in the fabric of space-time were amplified to cosmic scales. These fluctuations produced two things. First, density fluctuations in matter, which we see as the hot and cold spots in the cosmic microwave background. Second, gravitational waves, ripples in space-time that have been propagating through the universe ever since. These primordial gravitational waves, if they exist, would be a direct signal from the moment of inflation from less than 1 second after the Big Bang. Detecting them would be an incredible achievement. They would tell us about the energy scale of inflation, the physical processes that drove it, and the conditions at the very beginning of the universe. But detecting primordial gravitational waves is incredibly difficult. They're very faint, much fainter than the gravitational waves from black hole collisions. They leave a subtle imprint on the polarization of the cosmic microwave background, twisting the direction of the microwave light in a particular pattern called B-modes. Several experiments are trying to detect this B-mode polarization. Telescopes in Antarctica, high-altitude balloons, and space-based missions are all searching for the signal. As of now, they haven't found it yet. There have been false alarms. In 2014, a team announced they'd detected B-modes, but further analysis showed the signal was actually from dust in our own galaxy, not from primordial gravitational waves. The search continues. And if primordial gravitational waves are detected, they would be the oldest signal we've ever observed. They would come from literally the first instant of cosmic time, from the moment of inflation, less than 1 second after the Big Bang. That would be the ultimate prize in our journey from young to old. We would have traced cosmic history from newborn stars forming today, back through ancient stars 13 billion years old, back through the first galaxies and quasars, back through the dark matter structures, back through the cosmic microwave background, all the way to the very beginning, to the moment of the Big Bang itself. But even if we haven't detected primordial gravitational waves yet, we've still come an incredible distance in our journey. We've traveled from objects that are hundreds of thousands of years old to signals that are 13.8 billion years old. We've seen newborn stars and ancient galaxies. We've traced the history of the cosmos from the present day back to its infancy. Now, as we approach the end of our journey, let's take a moment to reflect on what we've learned and what it all means. Standing here at the end of our journey through cosmic time, it's worth thinking about what we've discovered. We've traced the universe's history from the youngest objects, stars still in the process of forming, to the oldest signals, light from 380,000 years after the Big Bang. In doing so, we've learned something profound. The universe has a history. That might sound obvious, but it's actually a relatively recent realization. For most of human history, people assumed the universe was eternal and unchanging. The stars were fixed in place. The cosmos was static. It wasn't until the 20th century that we realized the truth. The universe is expanding, it's evolving. It had a beginning, and it will have an end. And everything we see around us, every star, every galaxy, every atom, has its place in that cosmic story. Think about the scales of time we've discussed. Human history goes back maybe 10,000 years if we're talking about recorded civilization. The history of life on Earth goes back about 3.8 billion years. The Earth itself is 4.6 billion years old. The Sun is also 4.6 billion years old. The oldest stars in the Milky Way are about 13 billion years old. The universe is 13.8 billion years old. Those numbers are hard to grasp. Let's try another comparison. If we compress the entire history of the universe into a single year, with the Big Bang happening at midnight on January 1st, when would different events occur? The cosmic microwave background, that signal from 380,000 years after the Big Bang, would be detected on January 1st at about 0.2 seconds after midnight. The first stars would form around January 12th. The first galaxies would assemble by late January. The Milky Way would begin forming in February. Our solar system wouldn't form until September 1st. Earth's entire history, 4.6 billion years, would be compressed into 4 months. Life on Earth would emerge by mid-September. Dinosaurs would appear in late December, around December 26th. They'd go extinct on December 30th. Human civilization, all 10,000 years of it, would occur in the last minute of December 31st. The pyramids of Egypt would be built 15 seconds before midnight. The Roman Empire would rise and fall in the last 10 seconds. The modern scientific era, everything from Galileo to the present day, would occur in the last 2 seconds. That's the scale of cosmic time. Human history is a tiny blip at the very end. Even the Earth's entire existence is only the last third of the story. And yet, in that tiny blip, we've managed to figure all of this out. We've measured the age of the universe. We've mapped the cosmic web. We've found galaxies billions of light years away. We've detected gravitational waves from colliding black holes. We've taken baby pictures of the universe from when it was 380,000 years old. That's remarkable. It speaks to the power of human curiosity and the scientific method. We're a species that emerged on a small planet orbiting an ordinary star in an unremarkable part of the galaxy. And we've managed to understand the cosmos on the largest scales imaginable. But our journey through cosmic time also raises some interesting questions. For instance, what is the fate of the universe? We've traced its past, but what about its future? The answer depends on dark energy. Dark energy is a mysterious force causing the expansion of the universe to accelerate. We don't know what it is. It might be the energy of empty space itself, or it might be something else entirely. But we know it exists because we can measure its effects. If dark energy remains constant, the universe will continue expanding forever, getting colder and more diffuse. In about 1 trillion years, all the stars will have burned out. In about 10 to the 100 years, black holes will evaporate through Hawking radiation. In the unimaginably distant future, the universe will be a cold, dark, nearly empty expanse, with only occasional particles separated by vast distances. That's called heat death, the eventual fate of an ever-expanding universe. It's not a pleasant picture, but it's billions upon billions of years in the future. For now, the universe is still vibrant and active, still forming stars, still creating structure. Another question that comes up is whether we're alone. In all of cosmic time, in all the billions of galaxies and trillions of stars, are we the only intelligent life? We don't know. We've found thousands of planets orbiting other stars. Some of them are in the habitable zone, the region where liquid water could exist on the surface. But we haven't detected any signs of life yet, intelligent or otherwise. Given the age of the universe and the number of stars, it seems statistically likely that life has arisen elsewhere. Some of those stars are billions of years older than our star. If life formed around them, it could be billions of years more advanced than us. Such civilizations would be unimaginably beyond our current level. Or maybe we're alone. Maybe life is incredibly rare, requiring such specific conditions that it only happened once. We simply don't know. What we do know is that the universe is vast, ancient, and full of wonders. Every object we've discussed tonight, from newborn protostars to ancient quasars, from nearby planets to the cosmic microwave background, they're all part of a single interconnected story. The story of how the universe evolved from a hot, dense state shortly after the Big Bang to the rich, structured cosmos we see today. And we're part of that story too. The atoms in your body were forged inside stars. The calcium in your bones was created in a supernova explosion. The oxygen you breathe was produced by massive stars billions of years ago. You are, quite literally, made of stardust. When Carl Sagan said, "We are a way for the cosmos to know itself," he wasn't being poetic, he was being literal. The universe, through billions of years of evolution, has organized itself into structures capable of understanding their own origins. Stars formed, planets formed, life emerged, intelligence developed, and now, here we are, looking back through time, understanding where we came from. That's a profound realization. It's humbling and empowering at the same time. Humbling because we're so small in the grand scheme of things. Empowering because despite our smallness, we can comprehend the grand scheme. We've reached the end of our journey, from the youngest objects in the universe to the oldest signals we can detect. We started with protostars forming in molecular clouds, newborn planets glowing with the heat of their formation, and supernova remnants expanding from stellar explosions. We moved through middle-aged objects like our own sun and solar system, 4.6 billion years old and thoroughly ordinary. We continued to ancient stars in globular clusters, 13 billion years old, witnesses to nearly the entire history of the cosmos. We found the first galaxies, assembling 300 million years after the Big Bang. We discovered quasars powered by supermassive black holes that formed impossibly quickly in the early universe. We traced the cosmic web of dark matter, the invisible scaffolding that shaped where galaxies formed. We looked at the cosmic microwave background, the oldest light in the universe, showing us what the cosmos looked like 380,000 years after the Big Bang. And we discussed primordial gravitational waves, ripples in space-time from the moment of inflation, the ultimate goal in our quest to see the beginning. Along the way, we've learned that the universe has a story. It's not static, it's not eternal. It began, it evolved, and it will end. But within that story, incredible things have happened. Stars have formed and died. Galaxies have assembled and collided. Elements have been created. Life has emerged. And through it all, there's been an arrow of time, a direction from past to future. The universe started hot and dense, and has been expanding and cooling ever since. Entropy has been increasing. Structure has been forming, and will eventually decay. This journey through cosmic time reveals something profound about the nature of the universe and our place within it. Every object we've discussed exists not in isolation, but as part of a continuous story of cosmic evolution. The youngest protostars forming today are made from gas enriched by ancient stars that died billions of years ago. The iron in their cores, the oxygen in their atmospheres, the carbon that will someday form planets and perhaps life, all came from supernovae that exploded before the sun was born. The universe is recycling itself, generation after generation, building complexity out of the ashes of previous generations. It's a cosmic cycle of death and rebirth that has been ongoing for nearly 14 billion years and will continue for billions more. We are part of that story too. The atoms in your body were forged inside stars billions of years ago. Some came from massive stars that exploded as supernovae, scattering their contents across light years of space. Some came from smaller stars that gently shed their outer layers at the end of their lives. The calcium in your bones might have been created 8 billion years ago in a star that no longer exists, somewhere in a distant galaxy that merged with the Milky Way long before Earth formed. The iron in your blood might have come from a supernova that exploded 6 billion years ago, long before the sun formed, scattering atoms across hundreds of light years of space. In a very real sense, you are made of stardust. You are the universe becoming aware of itself, a collection of atoms that has organized itself into a pattern capable of understanding its own origins. The atoms that make up your brain were once floating in interstellar space, were once part of a cloud that collapsed to form the sun and planets, were once scattered across the asteroid belt, were once brought to Earth by comets and meteorites, were once incorporated into living organisms, and now they're arranged in a pattern complex enough to contemplate their own origins. That's extraordinary. But for now, in this brief moment of cosmic time, the universe is alive with activity. Stars are forming, planets are coalescing. Maybe somewhere out there, on a planet orbiting another star, other beings are looking up at their night sky and wondering about their place in the cosmos, just as we are. Maybe they're tracing the same journey from young to old, from nearby to distant, from present to past. Maybe they're realizing, just as we have, that they're made of stardust too. The journey from young to old, from newborn stars to the cosmic microwave background, is really a journey of understanding. It's about figuring out where we came from, how we got here, and where we're going. It's about our place in the vast tapestry of space and time. It's about recognizing that we're part of something much larger than ourselves, a cosmic story that began 13.8 billion years ago and continues today. And it's a journey that's far from over. Every year, we discover new things. New exoplanets orbiting distant stars. New ancient galaxies from the early universe. New insights into dark matter, dark energy, inflation, and the fundamental nature of reality. The James Webb Space Telescope is just beginning its mission, and it will undoubtedly find even older galaxies, even more distant quasars, pushing back the frontier of our knowledge even further. Future missions might detect primordial gravitational waves, giving us a direct window into the moment of inflation, the first fraction of a second after the Big Bang. Future telescopes might image Earth-like planets around other stars and detect signs of life in their atmospheres. Future generations might answer questions we haven't even thought to ask yet. The story of the universe is still being written, and we're privileged to be a part of it. So as we conclude this journey through cosmic time, take a moment to appreciate the incredible fact that you're here now, able to contemplate these things. You're made of atoms created in stars billions of years ago. You're living on a planet that formed 4.6 billion years ago. You're part of a species that emerged only recently, but has managed to understand the cosmos on the largest scales. Look up at the night sky tonight. Every star you see is a time machine, showing you light that left years, decades, centuries, or millennia ago. The Andromeda Galaxy, visible as a faint smudge to the naked eye, is showing you light that left 2.5 million years ago. You're seeing it as it was, when our ancestors were learning to walk upright on the African savanna. And if you could build a telescope powerful enough, you could look even farther back. You could see galaxies as they were 10 billion years ago, when the universe was young and the Milky Way was still forming. You could, in principle, look all the way back to the cosmic microwave background, to 380,000 years after the Big Bang. The universe is an archive, and we're learning to read it. Every new discovery adds another page to the story. And that story, the story of cosmic time, from the youngest objects to the oldest signals, is the greatest story ever told. Thank you for joining me on this journey. Keep looking up, keep asking questions, and remember, we're all made of stars, and we're all part of this incredible cosmic story. The universe is 13.8 billion years old, and it's still full of mysteries. What a time to be alive.